We've seen that the equilibrium constant can be written in terms of this reference parameter of delta R G0, and that this in turn can be written as a summation over all of the reaction species times their stoichiometric coefficients times their reference chemical potential. Now I could also write this as a summation over those coefficients times their stoichiometric coefficients times their molar Gibbs energy. But that raises a question. What is this quantity? What is this thing that we may want to use? Because we ultimately will want to calculate, if you will, the equilibrium constant that is written as this function of this quantity. So is there a way that we can tabulate values for this that will allow us to calculate this readily for any reaction? Well, I'll remind you that Gibbs energy does not have an absolute scale. There's no point at which we can say definitively Gibbs energy is 0 at this point, as we can for temperature at absolute 0 Kelvin, or we can say for pressure when there is no force per unit area being exerted on a container. All right, so Gibbs energy, and this is also true of enthalpy and internal energy. At best we can do is to measure relative changes of those quantities relative to some reference standard. Well, we saw that earlier that we could develop a reference standard for enthalpy that looked something like this. We would define heats of formation that basically corresponded to a reference set of chemical equations. So reference set of reactions that were the formation of each species from their component elements, with their component elements all in their standard states. All right, so we could do this to set up basically a scale for enthalpy. Can we do something similar for Gibbs energy? Well, in fact, we can, and we're going to borrow off this idea for enthalpy to get there. Now, I'll remind you that Gibbs energy is related to enthalpy, but it's also related to entropy. So we're going to need to include entropy in this somehow. But entropy now is one of those things that has absolute values. So when we talk about S0, that is an absolute entropy that can actually be calculated explicitly from 0 Kelvin all the way up to whatever temperature you want. Okay. The one thing we have for this absolute entropy, though, is that at 0 Kelvin, we define that absolute entropy to be equal to 0, and that's the third law of thermodynamics. All right, so how can we use this reference value for enthalpy and this absolute entropy, to develop a reference system for the Gibbs energy? I think the best way for me to relay this is to use an illustrative example. And hopefully the example will make sense and will allow you to understand sort of where certain tabulated values for Gibbs energy come from. And the example I'm going to use is to look at benzene. So what we're going to do is we're going to define something called the Gibbs energy of formation for benzene. So in other words, a factor that looks something like this. Okay, which is, if you will, the Gibbs energy equivalent to the heat of formation that we had up here for enthalpy. Now I'll remind you that if we're looking at a formation reaction for benzene, that would involve combining carbon and hydrogen gas. Those are the only two elements we find in benzene, and creating benzene, which of course is C6H6. Now, I'll also say that benzene is a liquid under standard conditions, so that is its standard state. Carbon is graphite, and we're going to need 6 of them to balance this equation. I'm going to need 3 of these hydrogens to balance this equation. So what I want to do is use this to figure out some kind of reference value for the Gibbs energy for this reaction. Now I'll start by saying that the heat of formation in this case is simply 49.1 kilojoules per mole. All right, so this gives us a starting point, because we know once we have the enthalpy for this reaction, all we need to do is figure out the entropy and we'll have the same thing. So what do we do for entropy? All right, well, as I mentioned, entropy is on an absolute scale. Okay, and so that means there are actual values. There is an actual value of entropy for benzene at 298 Kelvin. Is that what we would use? Well, I'll sweeten the pot a little bit, if I may, by saying that that will refer to the absolute entropy of this quantity in this reaction at 298 K. But there are also non-zero values for the absolute entropy of graphite at 298 K and of hydrogen gas at 298 K. Okay, let me fill in what those values are. For something like the carbon and graphite form, it's 5.7 joules per mole Kelvin. For hydrogen gas, it's 130.7 joules per mole Kelvin. And for benzene, it's actually 173.4 joules per mole Kelvin. So if I have these three values, I can figure out what the change in entropy will be for this reaction. I can do it the same way that I do it for enthalpy. So for example, the change of entropy for this reaction, we'll call it the entropy of formation for benzene. All right, is simply going to be the absolute entropy of benzene. All of these are at 298 Kelvin, minus 6 times the absolute entropy for graphite, minus 3 times the absolute entropy for hydrogen gas. And when I get through adding all of these things up, I see I've mixed this. I should have put absolute entropy for hydrogen gas here. But when I plug in my values for benzene and for graphite and do this calculation, I'll find that the entropy change for this process would in fact be negative 252.9 joules per mole Kelvin. All right, so I have an entropy change for this process written here. I have an enthalpy change for that process written here. So with these two things, I can define what the Gibbs energy change is for this reaction of formation, right? And that Gibbs energy change of formation for benzene will be equal to the heat of formation for benzene minus T times the entropy change of formation for benzene. Now what temperature do I use? Well, I use the standard temperature, 298 Kelvin. So I'll have that this is equal to 49.1 kilojoules per mole minus 298 Kelvin times negative 252.4 joules per mole Kelvin. Actually, I should have had the parentheses on the outside there. All right, so when I figure all this out, I'll end up with a value of 124.5, and this is in kilojoules per mole. All right, so this represents the free energy of formation for benzene. There's a decimal point there. All right, so this is a number that is tabulated. In fact, you can look this up in standard thermodynamic tables and you will find this number. You can calculate it the way I've outlined here and you will get that number. So I hope that gives you some reassurance that this is a real quantity. But what it also tells us is that this quantity that we have devised here is the thing that we can use for this standard or reference Gibbs energy change for a given reaction. Okay, I have done it for the formation of benzene, but now we can imagine if we have some reaction that is simply A plus B, going to C plus D, that we would simply calculate the delta G for this reaction in the same way that we calculate the delta H for the reaction using heats of formation. So we basically use a generalization of Hess's law and use the tabulated values for these free Gibbs energies of formation. And what we will get out of that is then the value for this reference standard for the Gibbs energy change for the reaction. And this is the value that we will then put into our expression for the equilibrium constant. So maybe to reiterate this Gibbs energy change for the reaction is simply going to be the sum over the stoichiometric coefficients times these Gibbs energy of formation values. All right, these things that, like the one I calculated here for benzene, but you would do the same process for each species in your reaction. Calculate this out. That will give you this value here, and from this you can then calculate the Kb value by simply plugging it in here, like that. So this is a really powerful, a lot of power that's been given you. You can look numbers up in a table, and as long as you know how to use those numbers, you can get the equilibrium constant for any reaction. Now, one thing I'll caution you is that this is the equilibrium constant for this reaction at a temperature of 298 Kelvin. And if you want the Gibbs energy, or you want the equilibrium constant at a different temperature, you're going to have to do a little bit more work. But we'll save that for another lesson.